All right, let's get started. Okay, so first off, sign-in sheet. You get that passed around. You all have a present for me today, right? Homework 3 is due today. Hopefully you all thought that was, it was a pretty short assignment. It wasn't really a lot to it. Uh, You'll see why here in a second, why I wanted you to have that experience, because you're going to have to do that and then, I guess a little, and then some on homework number 4. And I'm going to walk you through what's going on with homework number 4 here in a little bit. But that's going to be assigned today, or it is assigned. It's on Blackboard. It is due on Wednesday, February 21st. I'm giving you some time on that one because it is a little bit of a heftier assignment. Now, here's the thing. I'm not accepting late submissions on that one because of our schedule. We're going to have our exam review that day, so I'm going to, turn over the solution the moment I get it back. Moment, no pun intended. And then, just so everybody's aware, we have a celebration scheduled next Friday, not, in 4 days, but in 11 days. So on Friday, February 23rd, we have our first exam, okay, which is going to cover homeworks 1 through 4, and then everything up until the lecture today, or the topic today. Today we're going to be discussing one-way slab design, and then after one-way slab design, that's exam 1. Everything from one-way slab design back until the first lecture, that is our first exam. Sound good? Any questions? Yes. So example 8, yeah. Another thing, I'll go ahead and mention this. So Marshall hosts an event on campus called Engineering Career Day during E-Week. It's on Wednesday, February 21st. We could use some volunteers for escorting some of the students around. We'll have about like 150 high school students here on campus. There's a whole bunch of workshops going on. So if you're available, that would really help. There's going to be like potential employers stuff there. It'd be a good chance to rub elbows with folks that might be hiring you down the line, what have you. So if you're available, that would be great. And when I say morning, I mean like the early part of the morning. So it wouldn't conflict with this class or anything. All right, sound good? All right. So today I want to talk about one-way slab design. We'll get into the design procedures, get into an example. You'll find that if you know how to design a beam with a known cross-section, you pretty much know how to design a slab because it's basically the same thing. But I want to talk a little bit about the concept. I want to talk about, sort of tying it together. So what I got here is sort of a conceptual image of what a floor system would look like, okay? Now, up until now, what we've been discussing is we've been discussing the flexural elements, the beams, the girders, and what have you. Get around you there. All right. Now, the one thing that we're sort of ignoring is the actual floor itself, the actual slab. If you're looking at a floor system, you've got, when we did our takedown, you have beams framing into girders, girders framing into columns, columns going to the ground, but it actually really starts with the slab. The slab frames into the beams, which goes to, girders and so on and so forth. So we kind of need to talk about that. Now, I'm sure a question that's why are you using the word one-way? What do you mean by one-way slab? Well, the slabs that we're going to be designing in this class are one-way slabs because they are designed or intended to bend in one direction, that they bend one way. So this image here on the top would be a perfect example of the assumptions that we make for a one-way slab. So, it's sort of bending just in this one direction. And that's a pretty conservative assumption for design purposes. And that's what a one-way slab is. A two-way slab sort of bends, the mental image that I get in my head whenever I think of a two-way slab is almost like how a trampoline would bend, about how it kind of bends this way and that way. So, you have that bending going on in both directions. Now, there are advantages to using two-way slabs. Because you're transferring the load in 2 directions as opposed to 1, what you find is that if you design a one-way slab, and I'm just making up these numbers to give you kind of a scale, But let's say you design a one-way slab and you find that that slab needs to be 12 inches thick. An equivalent two-way slab might be something like 8 inches thick. You might be able to shave some weight off of that slab. And so there are some benefits to using two-way slabs. The problem is that two-way slab design is a little trickier. First off, the math, like if you're getting real analytical with it, the math gets way more complicated very quickly. And you kind of, this is one of those things where you need to learn how to walk before you can run. You need to learn how to do one-way slab design first before you can even think of tackling more complex issues. So we're going to keep it simple and keep it straightforward and start with one-way slab design. Now, the way that you design a one-way slab is pretty straightforward. Okay, so keep in mind a slab is nothing more than a really flat beam that's supported, on each end. So what I've got here on the bottom, I've got an image of a slab. Let's say that slab is sitting on a floor system. So this would be a beam, this would be a beam, and then this is the slab on top of that. What we do for design purposes is we say, all right, let's sort of, cut out of this a small little strip for design purposes. And for units, we usually take one that's a 1 foot wide strip. And we say, all right, let's do some math and some analysis on this strip and figure out how much reinforcement we need inside that strip. And then we say, all right, well, whatever reinforcement we need there, let's just repeat that pattern of reinforcement along the entirety of the slab. And that's basically the long and short of how we do slab design. We design this little strip, and whatever reinforcement we get, we just repeat that everywhere. Now, there's a couple additional details that you need to be aware of. So one of the details is that we're actually going to be providing reinforcement in two different directions. So what I'm calling our main steel, the steel that we're providing for structural purposes, is going to be designed just like we did in our previous example for a known cross-section. The temperature steel, which is steel that's going, I call it temperature steel, steel that's going in the opposite direction. We place that reinforcement there not really for structural purposes, but more to prevent cracking from things like day-to-day use, from thermal effects, from shrinkage of your concrete, etc. So there's going to be a layer of steel that we select for design purposes, and then there's going to be a layer of steel that we put in for thermal effects and shrinkage and things like that. Now, another thing worth mentioning, because your reinforcement is spread out over a much larger area, the cover requirements for slabs aren't stringent as they are for beams. So cover for slabs is about 3/4 of an inch. And what we'll do in most scenarios, if you recall, like for beams, we took the effective depth and we added 3 inches to get our height. For slabs, we'll add like 1 inch. So, just so you're aware of what's going on there. Now, the reason why we can design a one-way slab in pretty much the exact same fashion as we do a known cross-section beam is because you know the width, because the width is 12 inches. You're idealizing that 1 foot wide strip. And as for the height, we're basically going to be taking the height from ACI minimum. So you've actually seen this table before. We used this table before when we were estimating the weight of a reinforced concrete beam. So for instance, if you have a simply supported beam, the minimum height of that beam is L/16. Well, if you have a simply supported slab, the minimum height of that slab is L/20, right? So that'll be how we determine the thickness. So if you got the width and you got the thickness, you know what the beam looks like, so just get to design. So here we go. All right, so here's how you design a one-way slab. So first off, we've got to determine the factored moments on the beam. And I say beam because you know what the width of that beam is. It's 12 inches because you're assuming that strip. And the height is just the minimum height that we're going to take from ACI. So that one's pretty straightforward. And again, if you know what the beam looks like, you do not need to go about determining the self-weight of the, or you don't need to go about assuming the self-weight of the beam, because you can determine that from a calculation. You can just calculate it out. Another point that's worth mentioning, we are designing a slab here. We're not designing a beam. So what you'll find when you do the calcs is that your moments can actually be kind of small, okay, because you're dealing with a really small element and the loads applied over a really small area. So if you get bending moments, like when we did beams, we were getting bending moments that were something like, what, like 400-foot kips, 500-foot kips. I mean, we're going to do an example here where the bending moment's going to be 5-foot kips. That's normal for a slab, so don't think that's weird, okay? Because it's, you know, it's over a really small area. So just be aware of that. So 3-foot kips, 4-foot kips, 5-foot kips, totally normal. Okay. Next, we are going to assume a phi value. We're going to go through and do that. And then we calculate a rho for design purposes. Again, we're not using the 0.18 FC prime over Fy because you don't need to guess rho from, you know, you don't just need to pull a value out of thin air. If you know what the beam looks like, you can solve for what rho would need to be. Once you've got rho BD will give you the area required for your steel, and then you choose a reinforcement pattern that meets spacing requirements for slabs, and we'll get to that here in a second. One of the other things I'll point out now, let me find it. If you haven't broken this out yet, I would go ahead and break this out. This, if you recall, I gave you a reinforced concrete beam design aid and a reinforced concrete slab design aid. So just so everybody's aware, this is probably one of the easiest design aids ever to generate in Excel. Everybody in this room could probably do this in about 5 minutes. Let me explain how this works, okay? Remind me, what is the area of a number 1, or what is the area, I already spoiled it. What's the area of a number 9 rebar? No, number 9. Just the area of a number 9 is 1 square inch. Okay, so bear with me on this. If I took a number 9 bar in a slab and I spaced that at 12 inches, would you agree that I have 1 square inch per foot? Good? Okay, now, what would happen if I took a number 9 bar and spaced it 6 inches? What would be the area per foot? 2 square inches per foot, right? So for instance, if you look at the number 9 bar, let me see if my pen works. Okay, so right here, that is the area per foot if the spacing is 12 inches. If it's 6 inches, then the area is 2 square inches per foot. Make sense? So the closer the spacing is, the more steel you're putting in there. Right? That makes sense. If I've got my bars spaced very close together, that's more steel, right? So I just want you to know what this table represents. So I've got bar spacing over here on the left, and then based on your bar, there's your areas. It's that simple. That's literally all there is to generating this table. So we'll use this for design purposes here in a very short bit. Any questions? All right. Don't worry. I think you'll find this is pretty simple. In terms of spacing, for our main reinforcement, we just calculate that using our reinforcement ratio, just the same pattern that we've been doing. Your bar spacing has to be, so your maximum bar spacing is the lesser of either 18 inches or 3 times h. So you calculate 3h and 18, whatever's the smaller value, that's your maximum bar spacing. The idea is that, you know, you're designing a slab. I mean, you could probably find a reinforcement pattern that's great, but if you've got rebar that are 5 foot apart, then you've got weak spots in your slab. So you have to have at least, your reinforcement has to at least be spread out in some fashion. So that'll tell you what your maximum bar spacing is. Temperature reinforcement's really easy. It's just 0.0018 BH. It's very easy to confuse this. It's H, it's not D. So when you calculate your main steel, you're going to use rho BD. This is 0.0018 BH. So just be aware of that. That's easy to mess up. Now again, temperature steel, this is just an empirical relationship. This is just, you know, one of those, you know, adages. You know, you go out in the field, you know, do this for 10, 20, 30 years, and you find that this is a reasonable, and that's the limit that you find in the spec. So 0.0018 BH is your minimum requirement of temperature steel, and the bar spacing is the lesser of either 5H or 18 inches. Yes?
What's
the height, the total height. Remember H and D? So, all right. Everybody good? All right. So let's design a one-way slab, okay? Now, I've got here that the span length is 10 feet, but I want everybody to make sure they have a good conceptualization of what that means. You know, if we're talking about the span length of a slab, the span length of a slab is really how far apart the beams are, right? Because if you've got beams 10 feet apart, the slab spans between those beams. Does that make sense? So a slab span length and a beam spacing is the same thing. I just want everybody to sort of conceptualize that. So we're going to use 4 KSI concrete, 60 KSI steel. You all saw in our beam design example that if you start tweaking your FC prime, I mean, it affects your flexural capacity, but not a whole lot, you know, not as much as you would think. Okay? Now, live load, we're putting 200 pounds per square foot on this slab. Do you think that load is reduced or not? Say that again? Exactly. Anything over 100 pounds per square foot is non-reducible. So, so is that reduced or not? Well, you couldn't reduce it anyways. Anything over 100 pounds per square foot is not allowed to be reduced. That's something to be aware of. Another thing to be aware of, even if it is allowed to be reduced, there's another rule that states that you can't reduce if your tributary area is so small. We're talking about a slab element's only so wide and so long, so we wouldn't reduce anyways. Now, the only dead load is the slab self-weight, so there's no superimposed dead load on this. That makes our life a little easier. Okay, so far so good? Okay, now, so just so everybody's clear on this, so what we've got, and please bear with me, I'm going to do my best. All right, so we've got a beam, we got a slab sort of sitting on top of that beam, about like that, okay, and testing my 3D art skills a bit. All right, so, does that make sense? It's a little messed up, but it'll be all right. Okay, so keep in mind, we're assuming that this slab goes on forever, okay? But what I'm going to do is I'm going to isolate this I'm going to isolate a little strip. Look something like this. So I'm going to look at this cross section right here, and I'm going to design that as if it was a beam. Now this beam is 10 foot long, and so that 10 foot, this is what I was meaning when I was saying that a slab span length is basically a beam spacing. Make sense? Okay. Now when I do this design, remember this dimension right here, that right there, that's the 12 inches. Okay? So if I look at that cross section, what I've got going on is this. So if I zoom in on that sort of little blue shaded area, what I've got is this. So here's my beam. All right? And so this dimension right here, okay, that dimension is B, and that's 12 inches, okay? I'm going to have some steel in here. I don't really know what's going on with that steel just yet, but I know a couple things. I know that this dimension right here is D, and this dimension right here, bless you, I know that that dimension is H. Okay, does that make sense? Now, we don't know what that steel reinforcement, like we don't know what sizes and spacing that we're using yet. Just be aware of the dimensions. Now, let me explain this. Okay, now keep in mind, we still got that third dimension, right? So it's, this dimension here, we're talking about along the span length or along the beam spacing, okay? Now that rebar that we're designing, it goes along the span, right? That is the main steel. However, we are also going to provide steel in this direction. Hold on now. We're also going to provide steel in that direction. So that is our temperature steel. So I want everybody to understand the orientation difference. So main steel goes along the span length or along the beam spacing. Temperature steel goes in the opposite direction. That temperature steel is not intended to resist load. It's intended to prevent cracking from thermal expansion, from shrinkage, from day-to-day use, things like that. Sound good? Okay. All right. Now, if you understand that, then couple things. All right. Remember, we're going to, for cover, here's another thing I'll write. For cover, we're going to assume that H equals D plus 1 inches. Now, if you want sort of a visual explanation for that, here's sort of the idea. So here's your slab, here's your bar. We're saying that this dimension right here, that's my cover requirement, that's my 3/4 of an inch, but D goes from the top to the center of that bar. So to keep things simple, that goes up a little bit. If we just say D plus 1 inches, that'll account for most commonly used bars that we use for slabs anyways. So that's a pretty common, straightforward approach. Does that make sense? Did that make sense what I just said?
Now, do we have to worry about cover to the side of it too? Or?
That's a good question. Do you have to worry about cover to the side? I mean, yeah, but you also have to understand we're just basically determining a general bar spacing. Remember, whatever pattern we pick is going to go on forever. Like you're saying the side, this 12-inch strip was just like analytical. It doesn't really exist.
Sure.
So that's going to go on forever. You do have to worry about cover to the side. You can just take that first bar and just space it in enough. But it's usually not that big of a deal. That's easy to get around. That's a good question. Any other questions?
When you design this, how close do you think they could actually get it? We're adding 1/4 of an inch on top of 3/4. I understand we want to design it right, but in actual do you think they could do it?
I don't understand what.
I just don't they pour this in precast.
Are you talking about? How are they able to get an exact 3/4? Is that what you're asking? All right. Have you ever seen a rebar chair before? Okay. All right. I'll show you something real quick. That's a good question, and I do want to address that a little bit. Is there not Chrome on these computers? Who uses Microsoft Edge? Okay. So rebar chairs they can either be plastic or they can be they're usually sort of bent up pieces of wire. And the idea is you buy these things by the bulk, like something like this. And the idea is based on your bar size and based on your required cover, you can just pick them out of a catalog and buy hundreds of these things. So you can see these rebar chairs were selected to meet a given cover requirement. That's a good question. Does that make sense? So that's actually pretty easy to determine. You just buy the one that you need, and there you go. So. Yeah, I see what you're saying, and yeah, you would think, okay, there's some plastic there. We just sort of conservatively neglect that.
Can you go back to the example?
Example?
Yeah.
Yes.
All right, so we're analyzing a figurative strip going this way.
Yes.
We orientate, okay, this is the main, this is the tempered based on that strip.
Yes.
Now, if we were to do a strip going the other way, would that change the main and the
Well, yes, it would, but you'd also have to have a beam that way too.
Okay, so your main is going against
The
the
beam.
direction of your beam.
Yes,
Okay.
yes. So I mean, you're saying, think about it like this. In our assumption, so let me answer that two ways. In our assumption, we're assuming only one-way slab design because we're assuming our main supporting elements are going this way, which is usually the case because that's the way the beams are facing. If you wanted to assume the opposite direction, that's fine, but you'd have to have beams there. Otherwise, you'd have a beam floating in space and there wouldn't be anything there. That's point one. And point two, let me also be clear. One-way slab design is conservative. You end up getting probably more reinforcement than you need. So,
Okay.
make sense?
So your tempered goes in line with the direction of your beam.
Yes.
Okay.
Yes. Any other questions? All right. Okay. Let's get some math done. All right. So, step one is to compute our factored moments. Okay? Okay. Compute factored moments. All right. So, help me out. What is the width of this beam going to be, quote unquote? 12 inches. What is the height? But we don't know what
Your minimum requirement.
minimum height. Does anybody have that? What is the minimum height for a simply supported slab? L over 20. So what is that? Is that just 10 over 20? No. Units. This is 10 feet over 20. So you need to convert that. 12 inches per foot. So it's half a foot or it's 6 inches. So right off the bat, we've already determined how thick the slab's going to be. It's a 6-inch thick slab. Okay? So that's pretty easy. What's that?
Is our D 5 inches?
So yeah, so D is 5 inches. So if you want, you can go ahead and write that here. Although that has absolutely no bearing on the self-weight. It's just there. So, all right. Now, help me out. How do we determine the self-weight? Hold on, somebody else. How do we determine the self-weight? How have we been determining the self-weight all along? There we go, gamma BH. So the unit weight of the concrete times BH. So we weren't given a unit weight in this problem, so what should you assume? What's conservative? There we go. So I'm gonna in kips, I'm gonna say 0.15 kip per cubic foot. And you tell me what to write. By now you should know. You tell me. You could, yeah. You could say 1 foot and then half a foot. Or you could say 12 inches and 6 inches and, 1 foot squared over 144. That's fine too. Like you could say, 0.15 times 12 times 6 over 144 or 0.15 times 1 times a half. Either one's fine. You just got to be consistent is the only thing I would say. Say it again. 0.075 what? Kip per foot. Do I have a second on that? Okay. Now again, this is really small, okay? If you extend this out, it's only 75 pounds per foot. But again, this is a strip of a slab that's only 12 inches wide. So it's going to be tiny. That's okay. Don't get freaked out about that. That's almost kind of one of the reasons we're doing this example. So when you see these 4-foot kip moments, 5-foot kip moments, you don't get freaked out by it. Slabs are going to be tiny. That's okay. Now, I'm going to walk you through the live load, and this is actually kind of nifty, okay? So first off, remind me, okay? Let's sort of put this over here. What was the pressure load for the live load? Anybody remember? It was 200 pounds per square foot, or 0.2 kips per square foot. Make sense? Now, let's go back to what we did on homework 1. If you have, before we do any math, let's just think about tributary area. If I have a pressure load applied over a tributary width of 13 feet, how do I take that pressure load and turn it into a distributed load on the beam? Multiply by the width, right? Make sense? And the width would be 13 feet in that instance, right? Let me ask you this. What is the tributary width for this 12-inch strip of slab? It's 12 inches, right? So watch this. This is kind of nifty. So before you write anything, watch this. So I propose that we take the pressure load and we multiply it by the width. But watch what happens. So the pressure load is 0.2 kips per square foot. Now this is kind of nifty. What is B? Say it again. It's 1 foot. See, if you write 12 inches, you're taking this and you're taking 1 foot over 12 inches. So it's just 0.2. See, for a slab, whatever your pressure load is, like if it's 0.2 kips per square foot, the distributed load is just 0.2 kips per foot. And that's one of the reasons why we use a 12-inch strip, is so that pressure load, you can just go 1-to-1 and say it's kips per foot. Does that make sense? It's just a units trick, really. All right. Sound good? Okay. I'm going to do something a little, okay? I'm doing it for a reason, okay? You're going to go, why are you doing this? Bear with me. Trust me, I know what I'm doing. Okay, watch this. All right, so this is how we did this in a previous example. We said WU is 1.2 W naught plus 1.6 WL. So we factored our load. And just tell me what that is. Chug that out. That's a good, yes, we did. We had a superimposed dead load, but for this example, right here, the only dead load is the slab self-weight. So if you have another one, you would have a WD. You're exactly right. 0.41 kips per foot. And then what's MU? WU L squared over 8. What's L? Which is 10, right? Let me go ahead and write that one out. 0.41 kip per foot times 10 foot squared over 8. What does that come out to be? 5.125. Foot kips, right? Do I have a second on that? All right. Everybody with me so far? Now, everybody sort of watch up here and pay attention to this, because this is kind of important for your homework assignment. I want you all to pay attention to this. This is method 1. Just watch with me. Watch method 2. And it's going to seem silly, but you'll see why I'm doing this here in a second. Let's compute a dead load moment. And let's compute a live load moment. All right, somebody help me out with each of these. So what's the dead and what's the live?
Is 0.9375.
And what's the live load? 2.5 even? Now, let's take each of these and say MU is 1.2 dead plus 1.6 live. What does that come out to be? Get the same thing, right? 5.125. Okay. Now, I completely agree that on this problem, method number 2 is a waste of time, okay? But there's a reason why I'm saying that, okay? If I have, we're analyzing this as if it's a simply supported beam, right? Our dead load is what? A uniformly distributed load? Our live load is a uniformly distributed load. So because they're both the same, we can factor that and then compute a moment. But what if you have dead load that's distributed and live loads that are point loads? You can't do this, okay? Because it's not the same thing. You have to compute a dead load moment separately, a live load moment separately, and then factor that. I'm telling you this right now because it's going to happen on your homework assignment. And if you take those point loads and say, well, I got a 30 kip load in the middle and it's 20 foot long, that's about 1.3 kips per foot or whatever, and we'll just do that. I'm going to go, no, that is wrong. I even have it on the homework assignment as a hint to do this. And I'm going to pull it up here in a second. So don't do that. No. Make sense? Does this make sense, though? Any questions? All right. Okay. So, oh, whoops. Okay. So that's step 1. Do you all need any more room or any more time? All right. What's step 2? If we have MU, what's step 2? MN. Compute required MN. And what do we have to do for that computation? We have to assume something. A phi of 0.9. It's phi. That is a common phi, FIFO. All right. So MN required is MU divided by our strength reduction factor. I'll just call it that. So 5.125 foot kips divided by 0.9. And then we are going to adjust that. We'll go ahead and do that right now and convert it to inch kips. So what does that come out to be? Somebody over here. Somebody over here. Anybody got an answer? There we go. 68.33 inch kips. And again, that's a lot smaller than what we had on the beam problems. Like we were given like 6,800 inch kips. Again, This is a really tiny element with really tiny moments, so it makes sense. So step 3, compute required row. Okay. So what do we got? We got row required. Remember, not the 0.18 FC prime over Fy because we know what the beam looks like. 0.85 FC prime over Fy. 1 minus square root 1 minus 0.85, bless you, BD squared, and 2 MN required. So let's see if I can fit that all in one line. So 0.85 for KSI, 60 KSI. Remember the 1 minus square root 1 minus. That shows up twice. So 0.85 times 4 KSI times 12 inches times what is D? 5. There you go. 5 inches squared. Don't forget the squared. And then 2 and 68.33 inch kips. All right. Now remember, this is a reinforcement ratio, so it's going to come out tiny. That's okay. All right. Anybody have a reinforcement ratio handy? 393. Do I got a second on that? Again, they're small numbers. That's okay. 4, once you've got that, compute required steel areas. Okay, so watch this. Bless you. So AS required is row BD, whereas the temperature steel is 0.0018 BH. That's a very easy mistake to make, so just pay attention to that. So this is 0.00393, and that's 12 inches, 5 inches, and then we'll calculate that, and then AT required is 0.0018 BH. So 0.0018, 12 inches, and then 6 inches. Okay? Make sure you pay attention to that. So that's not a typo. That's correct, that those two dimensions are different. Okay? So what is the top one? 0.236. Do I have a second on that? Okay, so watch this. So that is 0.236. Now here's the thing. That's square inches of steel, but that's per foot of slab. And this bottom one comes out to be what? 0.1296, so maybe like 0.130 inches squared per foot of slab. What do you think? Any questions? All right. The only thing left to do is to actually pick some steel, okay? So we actually have to select some reinforcement. Okay. Now, before we do that, we need to make sure that whatever pattern of reinforcement that we pick makes sense. What I mean by that is bar spacing. If you recall, main reinforcement has a maximum bar spacing of the lesser of 3H and 18 inches. And for temperature, it's 5H and 18 inches. Blah. So the way that we do that computationally is we say, all right, we've got, for main steel, we have an S max, which is the minimum of 3H and 18 inches. Now, this is sort of serendipitous because what happens is the minimum of 3 and 6 inches and 18, well, what is that? It's 18 inches because 3 times 6 is 18. Now, for the temperature steel, we just need to make sure that S max is the minimum of 5H and 18 inches, which is, do better than that, the minimum of 5 times 6 inches, or 18, which is 18. So as long as our bar spacing that we pick is less than 18, we're good. Okay? So let's check that out. So I'm going to pull out my slab design aid. Let's check this out. Oh, we're doing great on time. Okay. So let's start out with the main steel. Okay? Now, let's say we had number 3 bars. How far apart would you space them? Think about that. Number 3. Let's just start off with number 3 bars. Say it again. Wait. I'm sorry, what? No, so over here is the area, okay? We have to provide 0.236 square inches per foot of slab, 5.5 inches. So options, so here are some options. Options for main. We have number 3 at 5.5 inches, and that's 0.24 square inches. What about number 4s? What would be a good spacing for number 4s? 10 inches. And that's 0.24 square inches. What about number 5s? Are there any viable options there? We could do 15 inches or something like that, but that would still be kind of larger, right? Right. So let me ask you a question. Let's say these are our only 2 options. You tell me, which one would you go with? They're the same area of steel, so why pick one over the other? Why? Okay, say number 4s. Why would you pick the number 4s? Less manpower. There's less labor. It's less labor intensive, right? You think. If you told somebody you have to place number 3 bars at 5 inches versus number 4 bars at 10 inches, and they both meet the spec, use the one that uses less steel. Because now that you've met the spec and you've met safety, let's keep it simple. So I propose that that's your best option for main steel. For temperature steel, what do you think we ought to go with? No, 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 no. We have a different area requirement. We could do number 4s at 18 inches apart. Does everybody see that? There you go. We'll use the same size. So I propose that for temperature, let's go with number 4s at 18 inches. All right. Does that make sense? So, just to draw, I know we're running short on time, but bear with me, okay? Just to draw a quick sketch of this slab, the slab is 6 inches thick, right? What we are providing is reinforcement this way, and we're providing reinforcement this way. This is number 4s at 18 inches, and this is number 4s at 10 inches. And this dimension here is 5. Now, I'm calling this a trial design because of what? What do we have to check? We have to check that phi equals 0.9, and we also have all those other reinforcement checks that we have to do, ASMN and all that stuff. So, sound good? Yeah. All right. Guys, 2 things. Number 1, this is it for exam 1, okay? Number 2, you now have everything that you need to do homework 4. Remind me at the beginning of class next time, and I'll mention a few things about homework 4, okay? Sound good? That's all I got. I will see you all on Wednesday.